Now with the same knowledge, let's get into binary. Before we go to the binary, one thing that you have to understand that in denary number system, we can write 3 because we wanted to write 3, or we can write 52 because we wanted to write 52, and then we can write 2317 or 62,548. We can write this way. What if you have this compulsion to complete every single digit in denary in a particular number of digits? What does it mean? It means that we have to write every number in 5 digits. So we will be like 00003, 00052, 02317, and 62548. So it means that we have to put these zeros here to complete the number of digits. All right, so it means that we have to put these zeros here to complete the number of digits. But that is not the compulsion, that is not the case. We can write it the way we like. If it is just a number which is comprised of 1 digit, we write 1 digit. If it is a number that is comprised of 2 digits, we write just 2 digits. We don't write more than the number of digits that we require to. But in binary, this is not the case. In binary, it is the compulsion that we have to write the binary number in certain amount of places. We cannot reduce that. Before we get into it, let's first understand binary the way we have understood denary. So in binary number system, or base 10 number system, base 2 number system, let's say we have got this number, zero, 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 one, 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 and 1. All right. How many bits are these? These are actually 8 bits. That's the first compulsion. You cannot write in computers a binary number which is not in multiples of 8s. Why in multiples of 8s? Because the least amount of data that a computer can save is a byte. A computer's byte is made up of 8 bits. Even if you like to save a single bit 1, you would have to save the 1 in the whole byte, and that means that every single digit that you are going to save should be in the byte. So that is why, although we wanted to save just these 4 ones, but we had to put all these 4 further zeros to complete the byte. So this is the first compulsion. All right, and then this binary number that you are looking at is actually having a base 2. So every single bit, the binary digit that you are looking at, is actually base 2. So this is base, and then position. So this is position. We discussed about positions in denary. Okay, now this base and the position as its power will give you the worth for binary digits. So those binary digits worth will be unit, 2, 4, 8, 16, 32, 64, and 128. 64 and 128. Now, what does it mean? It means it is simple that these words in binary are the result of this base and the position as its power. So every single number in binary is being treated technically the same as the denary number. But in denary, what happens that we have got unit, 10, 100 and 1000, where the base is 10. If the base is 10, it means that we are moving from right to left 10 times. Unit becomes 10, 10 becomes 100, 100 becomes 1000. Why? Because the base is 10. But in binary number system, we move from right to left 2 times. Unit becomes 2, 2 becomes 4, 4 becomes 8, 8 becomes 16, and 16 becomes 32, and then 32 becomes 64, 64 becomes 128. All right, and as we have done in denary number system, let's say this number 0, 0, 0, 0, 1, 1, 1, and 1. Every single bit is being multiplied with its worth. Every single bit is being multiplied with its worth, which is its positional weighting, and the results are found. And these results are then being added together. All right, so 8 plus 4 is 12 plus 2, 15 plus 1, 16. Sorry, 8 plus 4, 12 plus 2, 14 plus 1, 15. So as you can see that this 15 and this binary number, they are actually the same. But the thing is this is in binary form and this one is in denary form. All right, so same principle is applied. Same principle is applied. This is binary number and this is denary number over here, and they are the same. Okay, so when we have a binary number, we put the positional worth of every single bit underneath it, multiply every bit with its positional worth. Whatever the result that we have found, we add all those results together, and the result is actually the denary number. That is how it works for binary. All right, so that is how it works for binary. And we have this compulsion that we have to actually write every single number in 8 bits or multiples of 8 bits, maybe 16, maybe 24, maybe 32 and all. So don't actually write any binary number which is not in multiples of 8. So CIE expects you to write the answer in multiples of 8s. So it means that any number that you have in binary can be solved this way. Remember, there is another method, people call it LCM method, where you divide the denary number by 2 and then you find this binary, and when you go back again the table of 2 is being used. That is a way of doing it, but we will not be using it. We are actually using everything in relation to denary number system, because this will be worth it when we will be doing other conversions. All right, so other conversions means those conversions which are not actually number systems conversions, rather those are conversions from other types of data to binary. Anyways, so we will stick to this particular form of conversion. Now, let's say I have got another number binary 0 0 0 1 1 and 1 and 1. So this is a unit 2 4 8 16 32 64 and 128. All right, so all you have to do, you don't have to actually multiply and think about it that way. See, we have got only two possibilities in binary. Either it is 0 or it is 1. So every word, when it is being multiplied by 0, it gets nullified, it becomes 0. So we will not be actually having 0 any effect over the result, final result. So if 0 is being added to any other number, the number remains the same. So what we will do, all we have to do is to understand that whatever the worth that we have, if we actually whatever the word that we have above or below units, we will be adding those words and we will leave the rest. So we will be adding 16 plus 8 plus 4 plus 2 plus 1. All right, so this will become denary number 31. All right, 16 plus 8 24 plus 4 28 plus 2 30 plus 1 31. Similarly, we may have different binary numbers. We may have 1 1 1 0 1 0 0 0, and then we have got, let's say, 0 1 1 1 1 1 1 1. Then we may have 0 0 0 1 1 0 0 0. All right, so let's find out what are these numbers in ternary. That is very simple. All you have to do is to take the word above 1 and add them in a single binary combination. So this will be 32 plus 4, 36 plus 2, 38 plus 1, 39. All right, so this would be 39. If you add these 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, that would become 127. Similarly, if you add 16 plus 8, that would be 24. So that is very easy. All you have to do is to add the word above units together and you will get the denary answer. Rule is the same. What actually you were doing, you were actually multiplying every single bit with its underlying worth. And whatever the result that you get, you will add those results to find the denary number. So to avoid that big thing, large method, all we have to understand that we have in binary either zeros and ones. So if we multiply 0 with its worth, that will actually kills the worth. But if we multiply ones with the worth remains the same. And resultants are all those words which had 1 on it. So instead of doing the whole practice, rather we can understand this simply, and by adding all these words above ones be added together. So 16 plus 8 plus 4 plus 2 plus 1, that is 31. 32 plus 4, 36 plus 2, 38 plus 1, 39, and when we add these all, this becomes 127, and when we add these two, this becomes 24. Now, let's say we are actually converting few numbers. I want to tell you few things. So few tips for the fast conversion, since we won't be allowed to use calculators in exam. So in exams, calculators are not allowed. That is why. So let's say you have got all ones to the worth 8. After that, you have all zeros. So it means that all the ones are clubbed towards the right. So the value of these ones in denary would be the next worth minus 1. So you have got all ones together. Next worth is 16. So 16 minus 1 is 15. So this number is actually denary 15. Similarly, if we have got all ones clubbed together to this worth 32, it means these are actually next worth 64 minus 1, 63. All right. Similarly, if these are clubbed to 4 and afterwards these are all zeros, so it means that next worth 8 minus 1, 7, and you can calculate it always. So this is 4, 5, 6, 7. This is 8 and 4, 12 plus 2, 14 plus 1, 15. So this is 7. All right. So if all the ones are actually clubbed on the right side, then the next worth minus 1 is the value in denary of that binary number. All right. And that is how, if we have this number, you can tell that this is 128 minus 1. This is 127. All right. So that is how it works for all those numbers which are clubbed. Similarly, if you have got more zeros and less ones, in that case, what you have to do is actually you have to add ones, because you have got less ones and more zeros. So this is 8 plus 2, 10. And this is 16 plus 4, 20. What if we put all ones in all 8 bits? Let's get back to our question. 1, 1, 1, 1, 1, 1, 1, and 1. So it means that this is 255. This is 255. And you can see, if we go further beyond 1 byte, so 1 becomes 2, 2 becomes 4, 4 becomes 8, 8 becomes 16, 16 becomes 32, 32 becomes 64, 64 becomes 128, and then 128 will become 256. So if I put all ones to 128, what would be the next word? 256. 256 minus 1, this is 255. That is your number. So if you have got more ones and less zero, instead of adding all these numbers, all these words above 1, what we will do, we will rather add the worth of 0 and we will subtract that from 255. So 8 and 4 is 12. So 255 minus 12 is 243. 255 minus 12 will become 243. So instead of calculating and having ideas and all and feeling the use of feeling for the use of calculator, it is a good idea कि हम ये चीज समझ लें कि हमें जो है वो zeros को ऐड करके 255 में से निकालना है. So let's say अब हमारे पास यहाँ पर ones हैं, alright, और यहाँ पर हमारे पास zeros हैं. So अगर ये सारे ones होते, so it means that this would be 255, but what is actually happening? We have zeros worth 15. 18, 4, 12, and 2, 14 plus 1, 15. So let's deduct 15 from 255. So what we are left with? 240. All right. And in case if we have got mixed numbers, if we have got mixed numbers, let's say we have a 1 0, 1 0, 1 0, 1 0, and 1 0. All right. So let's say we have got 1 0, 1 0, 1 0, and 1 0. In that case, you are left with nothing but the calculation for every single word which is above 1. So this will be 170. So this is 1 0, 1 0, 1 0, and 1 0. Similarly, if we go with 0 1 0 1 0 1 0 1, in that case जो हमारे पास सिस्टम बन जाएगा वो होगा 0 1 0 1 0 1 and 0 1. That would be 85. 1 0 1 0 1 0 1 0. Yes, this is 85. Okay, so that is how the whole thing works. The last thing that I need to tell you is about this worth 1 means unit. So if this unit is 1, this means that number is odd. All right. So if this unit is actually 0, this means that number is even. All right. So this means that number is even. ठीक हो गया? So this is odd number. This is odd number, this is odd number, this is odd number, this is even number. This is even number. This is odd. This is odd. This is even. This is even. This is odd. You can check. All right. So 15 is odd, 63 is odd, 7 is odd, 127 is odd, 10 is even, 20 is even. Similarly, 243 is odd, 255 is odd, 240 is even, 170 is even, 85 is odd. All right. So these were few things that I wanted to tell you before we go any further with the conversions in hexadecimal.